Hello, we start with the last PowerPoint presentation for chapter number 10, gases. And this is the kinetic molecular theory. The main objectives for this is to understand the kinetic molecular theory as it is applied to gases, especially the distribution of molecular speeds, energy, understand the phenomena of diffusion and effusion and apply Graham's law, recognize why gases do not behave like ideal gases under some conditions. Deviations from ideal behavior are largest at high pressures and low temperatures. And so with these, we want, because of the deviations that are there, we need to understand what are the assumptions under the kinetic molecular theory that are not very accurate. And to do that, we go down to the next slide and continue. So kinetic molecular theory, or KMT, gives us why, not how. A model works for liquids and solids too. It predicts the behavior. Mathematical model, ideal gas behavior, is predicted by postulates. What are the postulates? Well, postulates, there are 5 postulates that are there, very simple to understand and comprehend. Gases consist of particles that are in continuous random motion. Volume of gas molecules is negligible in comparison with the total volume of the container. Attractive and repulsive forces between the gas molecules are negligible. The average kinetic energy is constant as long as the temperature remains unchanged, and the collisions are elastic. Average kinetic energy is proportional to the absolute temperature. Now, in order to behave, how does temperature affect the average speed? At 1000 degrees Celsius, the red line shows you how it behaves, and at the blue line indicates at 25 degrees. Under each curve, the same and proportional. Each area under each curve is the same and proportional to the number of gas molecules that are there. So initially, at very low temperatures, then few molecules have very few molecules have very low speeds. At 25, more molecules are moving at about 400 meters per second than at any other speed. That is at the 25 degrees. But when you change the temperature to 1000 degrees Celsius, then we find that more molecules are having the temperature of 1600 meters per second than when we compare it to the 25 degrees Celsius. This particular type of chart is called as a Gaussian figure, and this is a Maxwell's Gaussian chart graph indicating the speeds of molecules that are present at different temperatures. Now, again, there is a video here, kinetic molecular theory, and it's not going to work, so I'm going to remove it. Remove this slide so that you don't get confused. And then, now the next postulate is that at any given temperature, molecules of all gases have the same kinetic energy. But the kinetic energy is given by 1/2 mu squared, where u is the average kinetic energy. Molecules of higher molecular weight have lower molecular speeds, and those with lower molecular weights have higher molecular speeds, which is easy to understand. So when we look at this for different molecules, you can see the speeds at different temperatures, as well as the number of molecules present at various temperatures. At the beginning, there are few molecules. Then you find that as the mass is heavier, you have more molecules at 25. And then as you go around to higher temperatures, the molecules spread. We remember that from physics that kinetic energy is 1/2 the mass times the speed squared. Now, at any given temperature, this is a repeat slide, so we have come back to it, but this is a reminder, and it's nice to keep reminding ourselves that higher molecular weights will have lower speeds and lower molecular weights will have higher speeds. And it is derived from the physics kinetic energy expression E is equal to 1/2 mv squared. The molecular interpretations. So most of the gas molecules, when they move, there is empty space, and so they're easy to squeeze together. The PV relationship, pressure results from collision of molecules with the sides of the container. Larger volume, frequency of collision decreases, thus decreasing the pressure. Interpretation, continued with the interpretation. Temperature in chemistry is in Kelvin. Temperature and volume. To keep the pressure constant when molecules move faster due to increased temperature, container has to get larger, and the pressure-temperature relationship in a given volume. If temperature increases, then average speed increases, so more collisions will result in higher pressure. Molecular effusion and diffusion. Effusion is the leakage of gas through a small aperture. Diffusion is the spread of gas throughout the open space that is there. Now, effusion and diffusion both depend upon the speed of the gas that is there, basically because they are moving. And the rate is governed by what we call as Graham's law. The rate of effusion of a gas or diffusion of a gas is directly proportional to its root mean square velocity, where RMS stands for the root mean square velocity and M is the molar mass. This implies that heavier gas molecules will effuse slower than the lighter gas molecules. Again, this is not going to work. So here, there is a problem based on Graham's law of diffusion. Carbon dioxide effuses through a pinhole at a rate of 0.23 milliliters per minute at 25 degrees Celsius. Another gas effuses at the rate of 0.36 milliliters per minute. What is the molar mass of the unknown gas? We see that the molar mass of the unknown gas is equal to the molar mass of the carbon dioxide times the ratio of the rate of the carbon dioxide over the unknown gas squared. And so when we get it and we do put in the values and square it up and multiply by 44, we get 18.0 grams per mole, and that is water molecule. The Avogadro's hypothesis, gas pressure, temperature, Boyle's law, and kinetic theory. Avogadro's law, pressure is proportional to N when these are the factors. P is proportional to N when V and T are constant. P is proportional to T when N and V are constant. P is proportional to 1 over P when N and T are constant. So deviations from the ideal gas equation. Real particles have volume. Real particles interact via intermolecular forces. At high pressures and low temperatures, these factors become significant. So in the ideal gas equation, we write it as PV is equal to nRT, where R is the gas constant. Ideal gas is a hypothetical gas whose pressure, volume, temperatures are accurately described by the ideal gas equation. Real gases approach ideal gas behavior at low pressures and high temperatures. Real gases deviate from ideal behavior. High pressure particles close to each other, and therefore the pressure of the real gas is less than the pressure of the ideal gas because of force of attraction that may tend to hold them together. At low temperatures, low kinetic energy moves slower, attract forces become more important, relatively less volume than the theoretical model predicts. Particles really do have some size, and therefore we have to introduce or use another correctional factor for non-ideal behavior. And this was done by Van der Waal, and it's called as the Van der Waals equation. The Just Scientist Johannes van der Waals said that real gases needed a new equation to describe them, specifically a correction for excluded volume and a correction for molecular attraction. The volume exclusion is subtracted from the total volume, and the molecular attraction for pressure is added to the pressure. And therefore, the kinetic theory molecule. Gas molecules move in straight lines, do not lose energy when they collide with the wall or with each other, have essentially no volume, do not attract or repel each other. The average kinetic energy of a gas particle is directly related to the temperature in Kelvin. Gases that adhere to these rules are referred to as ideal gases. However, deviations from the ideal gas behavior makes corrections for the volume of particles and the intermolecular forces that exist. The A is a correction factor for intermolecular forces, N is a correction for B is the correction for the volume correction, N is the number of particles over there, and V is the volume of the container. When we open this equation up and rewrite it, we have P plus N squared over V squared, which is basically a concentration term multiplied by A, and that gives you the pressure correction, and V minus NB gives you the volume correction for the molecules. So now you have some self-study questions, and so you can attempt them. And with that, I'm going to stop my presentation because we have completed chapter number 10. So go through all the material and give yourself a pat on the back to say you've done real good.